theory. So Sven asked me to talk about theories of aging, and as already been discussed by the previous speaker, there are probably as much theories of aging as there are researchers working on aging. So I will try to give a kind of brief introduction so that some of the aspects that will be covered later in the program have had some introduction. Okay, so the first thing is, well, this has also been described by the previous speaker. So how could we characterize aging? I guess the best characterization is that we become more vulnerable, and that therefore our susceptibility to disease and in the end death increases. And there have been many theories to explain, well, how does this come and how does this work? And I think if you want to categorize the theories, the most broad distinction could be made by discriminating theories that actually try to provide an explanation for the why question. So why do we age? And this is mainly based on evolutionary biology. And then there are many theories that actually try to provide a mechanistic explanation about what are the mechanisms that drive aging. How does it work exactly? Well, to start with the why question, so with the theories that try to provide an evolutionary explanation, I will start by briefly introducing the concept, and that is the idea that in the end, genes in the gene pool are being selected based on whether they provide an advantage, yes or not. And if you would look at the survival curve in, let's say, adverse environment where our genome evolved, we can see that there's a very high power of natural selection towards traits that are expressed early in life, because a big part of the population, if we would say this is 100% survival, and here it's about 0, under this environment, actually there's nobody alive at the age of 100. So actually the force of natural selection, any trait that would enhance survival from the age of 80 to 200, there would be no benefit. So the idea is, well, there's only, let's say, a force of selection that selects traits that would actually confer a survival advantage early in life, because here, given the structure of this population, there is material for natural selection to work on. There are people around. Well, here most people have died already due to starvation, infectious diseases, famine, so there's not much to select on there. So that's the basic principle. And now we can see that all of a sudden our life expectancy has been changed, actually over the last 150 years. So all of a sudden we do no longer follow this course, where most of the population has already died, let's say before the age of 60, but we now can, in theory, become much more long-lived because we have improved, let's say, our environment. We have talked about vaccination programs, better health care, economic status has been improved, but still we do not live indefinitely. So somehow we hit a limit, and well, there are many theories that try to explain why we hit this limit, but the question is, why do we not live indefinitely? Why do we still, at some age, start dying, and then in the end, you know, the maximum lifespan so far is 122 years? Well, the idea is that this is because of evolved limitations in our systems for maintenance and repair, and there's actually many theories, but I will just highlight 3 of them. And the first has been proposed by Metabolism already in 52, and he said, well, you know, because of this decline in the force of natural selection with age, there has never been any selection against the occurrence of genes with deleterious effects at advanced ages in the gene pool. So they have not been cleaned out of the gene pool because of the fact that the force of natural selection declines. And therefore, now that we are living longer, we are facing, let's say, the adverse effects of those deleterious genes. Well, a second theory said that it's not so much the lack of selection against those deleterious genes, but it is more the fact that we have been selected for genes that confer an advantage early in life, and those genes may actually, when they are expressed later in life, have, let's say, deleterious late life consequences. For example, it could be good for you to, for example, be heavily invest in tumor suppression mechanisms early in life, but then maybe later in life, if because of those investments you get a depletion of stem cells or cells become senescent, you may actually pay the price for that, right? So that's the idea of antagonistic pleiotropy, that one feature may have different effects when it's expressed in a young individual or in an elderly individual. And then there is actually the disposable soma theory of Thomas Kirkwood, which kind of builds on this principle of antagonistic pleiotropy. But he states that there is actually a resource allocation problem, or at least let's say there is the idea that, you know, suppose we have a body that has a certain maintenance requirement, right? And then there's an amount of energy that we could invest in maintenance. Suppose that in theory, if you would invest all the available energy into the maintenance of the body, repair would be perfect and we could live forever. However, due to resource allocation problems, it's not beneficial to invest all the available energy into the body, and some of the energy might have been better spent, for example, on reproduction or on other bodily functions. So the disposable soma theory involves this, let's say, resource allocation problem. And then the idea is that given under the situation where the genome evolved, there was an optimum investment in maintenance, which was not sufficient actually for us to sustain a very long life. So there's a maintenance gap, right? The amount of maintenance that we require is not being sufficiently invested. And actually, Maarten Wensink, who worked in our laboratory for a while, who is now doing a PhD trajectory at the Max Planck Institute in Rostock, he said, well, you know, there can be many other trade-offs than the trade-off between investments in, let's say, reproduction versus maintenance. There could also be the fact, maybe, you know, our bodily plan has evolved in such a way that we can never maintain it, even if we would invest all the available energy in maintenance. Maybe, you know, it's advantageous to develop a much more complex body system, and maybe, you know, the maintenance gap cannot be bridged by just changing the reallocation of resources, right? It could be advantageous to have a more complex body. This may give, let's say, a survival advantage early in life. However, because the body requires more maintenance, you know, it could be that in the end of life, we hit this bottom sooner. So there could be, you know, there's still a lot of discussion ongoing. Is it an allocation problem? Or is it also, you know, the maintenance gap can arise actually in two ways. Either by taking away resources for the investment in maintenance, but also by increasing the requirement for maintenance. And depending on which one you would believe, you know, this also has implication for the way we should approach the aging problem. Okay, so this is all I wanted to say right now about the ultimate theories of aging, and there have also been many theories that try to explain the mechanisms of aging, and I will just highlight a few here. And well, I guess one of the most obvious things is that because of this maintenance gap, we accumulate damage. And there are many different sorts of damage, and actually Aubrey de Grey has categorized them into seven types of damage, 7 classes, which can relate to, you know, differences in the function of cellular, so either there are too many, too little, or cells become toxic. There can be damage to the DNA, which can be nuclear or in the mitochondria. There can be all sorts of aggregates in the cells or outside the cells, and there can be extracellular crosslinks, for example, due to glycation processes, which will be discussed, I think, in the next lecture. And actually, I guess that at the moment there's quite a lot of discussion ongoing on which of these types of damage is the principal driver of aging, and which mechanism then causes this damage, also with respect to how we, in the end, could tackle the aging problem. And I guess that at the moment the two main opposite theories include one theory which says, well, the main source of damage is being caused by our own metabolism, or, you know, and one of the most principal agents there would be the reactive oxygen species, which is the oxidative damage theory. And then there's also, and I guess that David Gemst will speak about this afternoon, then there is the alternative theory which says that aging is not primarily caused by macromolecular damage, but that it's mainly due to the dysfunction of cells. And that these cells start to dysfunction because of the overactivation of this growth-promoting pathways, which has been discussed by the previous speaker, like TOR signaling and insulin, IGF-1 signaling. And that there's a kind of continuation of these signaling pathways may have beneficial effects any longer in a individual, but when they go on into the later stages of life, they may actually lead to detrimental effects, as we can also see with cells that become senescent. Well, so within those theories that think that metabolism is, let's say, the principal driver, there are many different theories, of which these are just one of the three. And it started with the observation that actually, that there is, let's say, a linear relationship between species of the metabolic rate and lifespan, which has later on been disputed to some extent because there's also a linear relationship between body weight and lifespan. So then actually Harman in 1956 proposed that it's the key aspect of metabolism which may drive aging is this production of these free radicals, the reactive oxygen species. And then later on, it was also found that there's not always a linear relationship between metabolic rate and aging. There's, for example, the bats, which live much longer than ordinary birds, but which have a very high metabolic rate. And then the idea was, well, if it's not metabolic rate which causes aging, but if it is these free radicals or these toxic byproducts, then it's possible to have, let's say, a long life with a high metabolic rate as long as you uncouple, let's say, the metabolic rate to the production of oxygen species. And this is then called the uncoupling to survive hypothesis, that once you reduce this load of damaging byproducts, you could still live long with a high metabolic rate. This is then summarized in this slide. So the idea is then, based on this first set of theories, that metabolism may in the end influence lifespan through the production of lots of toxic side products, of which then the principal mediators would be the reactive oxygen species. This would then damage macromolecules. Cells could react to this damage by becoming senescent, for example. And this in the end would lead to tissue dysfunction and age-associated diseases like aging, depending on whether it's let's say mutagenic lesions which propagate, or whether it's, let's say, cytotoxic regions or cytotoxic regions which propagate. Well, like I said, I guess that the oxidative damage theory is being disputed at the moment, and I guess that David Gems will talk more about this. So the question is it mainly oxidative damage which drives aging, or is it all sorts of macromolecular damage, of which reactive oxygens are just one of the players, but there may be many others? And well, an alternative theory is that it is not so much, the molecular damage which causes aging, but the dysfunctioning at the cellular level, which might be due to this overactivation of signaling pathways, which on the one hand may result in this damage and also result in other aging-associated phenotypes. And this is just to set the stage. I guess a lot of the details will be discussed later within the program. So there will be talks about glycation, which can result in these crosslinks. There will be talks about DNA damage as the principal driver. The whole idea about whether it's ROS or TOR will be, I think, discussed by David Hems later. Talks about mitochondria, autophagy. So this was just, let's say, a kind of introduction to the details which will follow later. So I don't know if you have any questions at the time being.